we learned about buffers on Monday. And the relative amounts of acid and base is one factor that can influence how effective a buffer is. So, in bold here, this is an important statement. A buffer is most effective when the concentration of acid and conjugate base are equal. So, if we look at two 1-liter solutions of generic buffer, pKa of 5, and we're going to look at the percent change in pH when we add 0.01 moles of sodium hydroxide to each of them. So, solution 1, we have equal amounts of acid and base. Initial pH is 5. Here we have a fair amount of acid and only a little bit of the base. So if you look at these add up to the same number of moles, right? So it's 0.2 moles of one or the other, but here it's split evenly and here it is not split evenly. So if we look at the initial moles, we're adding 0.01 moles of base to this. We had 0.1 here and 0.1 there. So this is the smallest amount, so we subtract that from these things, add on that side. So afterwards, we have moles of hydroxide, moles of acid, and moles of conjugate base. And then we're going to calculate the pH of that solution. I think we can use Henderson-Hasselbalch. pH is pKa plus the log of base over acid. So the pKa for this buffer is 5 plus the log of the base concentration, the A minus, 0.110, divided by the acid concentration, 0.090. Here's my calculator. So 5 plus log of 0.11 divided by 0.09. New pH 5.0872. So what we're going to look at here is the percent change. So the percent change will be the new one minus the original divided by the original times 100. And so that gives us 1.743, 1.7% change. So let's look at our second buffer, solution 2. Again, we're adding 0.01 moles of hydroxide. These are our initial amounts. We subtract from the reactants, add to the products. We end up with these for our moles after. Does anybody have any questions about that table and how that table works? Moles initial, change moles after. This is a way of making the stoichiometry of this more visible, more visual, I should say, so that we can see what we're doing. So after we add the hydroxide, we're going to have these new amounts. And so then we can calculate the pH of this one. So this is going to be, It's got the same pKa. And again, log of base over acid, the base is 0.03. The acid is 0.170. .2467. So the percent change for this one what? I think I did something wrong. Or x is small is not valid. I'm adding hydroxide. Oh, never mind. This was the initial pH. Okay. I was like, wait, it went down. No, the initial pH was lower. Okay, phew. Okay. So I'm going to take the new pH and I'm going to subtract the original, which was 4.05 here. And here we get 4.9% change. So we have a larger percent change in our pH. We could also look at the absolute change. This one increased by 0.09. And that one, increased by 0.2. So delta pH 0.09 for that one. Delta pH 0.20 for this one. Let's go back and look at the previous slide real quick. Yeah. Any questions? This buffer is more effective. When I add hydroxide to it, the pH only changes a tiny bit. Over here, this pH is going to change more significantly. And, 0.2 doesn't seem like a lot, but that's an exponential scale. And so that is a big change. So to be reasonably effective, this is our guideline. The relative concentrations of acid and base should differ by less than a factor of 10. Or stated another way, if you take the ratio of base to acid, it should be between 0.1 and 10. One should be no more than 10 times the other. And that will give us a reasonably effective base. Why not just always have them equal? Well, sometimes we want the buffer to be at a different pH than the pKa of the buffer. And so in order to get that, we have to tweak the amounts a little bit. So the ratio relative amounts is important, and the absolute concentration of the acid and conjugate base is another factor. So the buffer is most effective when those concentrations are high. So here we're going to look at that same buffer, but now solution 1 has concentrations 10 times higher than solution 2, and again we're going to calculate the percent change in the pH when we add 0.01 moles of sodium hydroxide. So we've got this all written out for us. So here we have 0.5 moles and 0.5 moles, and here we have 0.05 and 0.05. These are both going to have a pH of 5 because the concentrations are equal. Here we're adding the 0.01, so we do our little table here and we get our new amounts, and then we use the Henderson-Hasselbalch equation. So the pH of that new solution is 5.0, the pKa, plus the log of the base, 0.510, divided by the acid. .017.4. So the percent change, 5.0174 minus 5 divided by 5. .35%. And then we're going to look over here, adding the same amount of hydroxide, but now we have smaller amounts of our conjugate acid or acid and conjugate base. So when we do the Henderson-Hasselbalch equation, now we have 0.06 for the base and 0.04 for the acid. And this changes 5.1761. Which is 3.5%. So the percent change is 10 times larger because these concentrations are smaller. The relative amounts are perfect. That's the best you can get, equal amounts. But these concentrations are low and these concentrations are higher. Higher concentration gives you a more effective buffer. Any questions? So a buffer will have an effective range. The lowest pH will be when the base is 1/10 of the acid concentration. And so when we do that, if you look at, well, what's the pH there? The pH there will be the pKa plus the log of base, which is 0.1 times acid, divided by the amount of acid. So I'm doing the base over the acid, but here the base is equal to 1/10 of the acid, and so those guys cancel out. And I end up with pKa minus 1. The highest pH will be when the base is 10 times as big as the acid. Again, the acid concentrations cancel out, and this gives us pKa plus 1. Not going to make you calculate that on a test. So the effective range of a buffer is its pKa plus or minus 1 pH unit. Another highlightable statement. So effective range for buffering system, 1 pH unit on either side of the pKa. So when we are trying to make a buffer solution, we know, oh, we want it to be this pH. We need to choose our buffering system. And so we want to choose a buffer that is going to have a pKa that is close to the pH that we want, because that'll give us the biggest range. Sometimes you can't find a buffer that is just right. So then you can tweak the pH of the buffer by altering the ratio of base to acid. But we don't want to get too far. We don't want to have one more than 10 times the other, because then we're not as effective. Okay, which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? So when they say sodium salt, let's think of it this way. So we could represent the acid as HA, right? And to make this buffer, we need the weak acid and its conjugate base. Can we add just anions to a solution? No, we can't. You can't have a beaker of just negatively charged things. Nature really hates that when you separate charges. Think lightning, right? They get back together forcefully. Well, so how do we get this into the solution? We use a salt, like Na, A minus. When we put this in water, it dissociates completely. Yeah, there's sodium ions in there, but they're not going to do anything. Sodium doesn't get involved in anybody's business. It just hangs out at the party. So the acid and its sodium salt, that's what they mean by that. So we want the buffer to be pH 7.35. Which of these would be the best choice? The one that's closest, its pKa is closest to the pH. Which one is that? The last one, right? They didn't, make us struggle too hard on that. The first ones are all 3 something, and this is 7, and we want 7.35. So that's our choice. Okay? Now this is a very practical question. If you have 500 milliliters of a 0.1 molar solution of that acid, what mass of the sodium salt do you need to make this buffer? Well, we know how to convert mass and moles, right? We're talking about the sodium salt of that. Whoops. Pushed the wrong button. So that's going to be NaClO, right? So we could calculate its molar mass, 22.99 plus 35.45 plus 16, 74.44 grams per mole. So we're trying to find grams of sodium hypochlorite. Well, what do we need to find before we can find the grams? What does this allow us to convert between? Grams and moles. So if we knew the moles needed of NaClO, then we could figure out the mass. How can we figure out the moles? Well, We want the pH to be 7.35. The pKa is 7.54. We're going to use the Henderson-Hasselbalch equation. pH is pKa plus the log of the base over the acid. Do we know the concentration of the acid? Yeah, it says it's 0.1. We know pKa, 7.54. We know the pH that we want. We can solve for the concentration of the base. So we're going to use, we need the molarity, moles per liter of sodium hypochlorite. So we can plug these things in. Desired pH 7.35, pKa 7.54, plus log of the base concentration, that's what we're trying to find, divided by the acid. If you're good with algebra and logs don't bother you, you can rearrange this and stick this into your calculator and get the answer, no problem. A lot of people can't do that. That's fine. Use the number solver. You can put this into the number solver. The base concentration here is your X, and you can get it to do all the icky algebra for you. So I did it in my head kind of way because I have had to keep up on certain aspects of algebra because I do them all the time. Anybody do the solver? What'd you get?
0.064565.
Okay, 0.064565. Yeah, and what I've got here is 0.064565423. So rounding, it comes out exactly the same. And they should match because we're not doing an approximation here. This is just solving for X. Okay, so that's the concentration of sodium hypochlorite. How do we find the moles that we need? Well, this guy here is really a conversion factor. It's not a starting point. We're going to start with milliliters of the solution. And we're going to use this as a conversion factor. So 500 milliliters, this is a place where millimoles is not going to help us. Let's change color here. $500 milliliters. We want to change that into liters. So review metric conversions. We want liters over milliliters so that the units cancel out. The bottom, the denominator, has the prefix milli. I'm going to write what it means on top. Milli stands for 10 to the minus 3. So 1 milliliter is 1 times 10 to the minus 3 liters. Then I want liters to cancel out, and I'm going to get to moles, and that's going to be the concentration I just calculated. So the liters cancel out. And then I want to get rid of moles, and I want to get to mass. And so this is where I'm going to use my molar mass, 74.44. You can also look at 500 milliliters and say, well, that's half a liter. That's fine. Just don't tell me it's 500,000 liters, please. So I've got 0.5 times 0.06457 times 74.44. 2.403 grams. And we really only have 2 sig figs going on here. So when we go to weigh this out, we're just going to try to get close to 2.4. We don't need to get 2.403. Any questions? This stuff down here, we all did in Chem 1A, right? We even put things together like this in Chem 1A. Now, the summer was a really long time, right? So you might be kind of rusty on that. There's going to be more of this, okay? So brush that part off. If you need a review, I've got videos on YouTube, or you can find other people's videos on YouTube about dimensional analysis. The new thing that we learned here is how to find this concentration. So we talked about things that affect the buffer capacity or the effectiveness of a buffer. So what do we mean by buffer capacity? It's the amount of acid or base that you can add without causing a large change in pH. And of course, you know, what is a large change? Well, this is a very qualitative word. But the buffer capacity will increase with increasing concentrations of your components, the acid and conjugate base. It will also increase as those concentrations become more similar to each other. So that's what we just talked about. Acid and base concentrations are equal, that's the best, and the concentrations are higher is better. Sometimes you know that your buffer is mostly going to have to neutralize acids or mostly going to neutralize bases. You kind of know what's going to come into it, and so you can anticipate the problem. So if we mostly have to neutralize acids, then we're going to put more of the base in there. If we mostly need to neutralize bases, we'll put more of the acid component in there. So here's an illustration of a concentrated buffer and a dilute buffer. There's just, you could think of these as little workers here. They're here to take care of the problem. There just aren't as many here. Once they take care of, they can only each take care of one guy. Once they take care of their guy, they're done. And so here, you could overwhelm this buffer by adding 3 molecules, right? Whereas this one has a lot more, and so you could add a lot more without destroying the buffer. Okay, we have a 1 liter buffer. It's 0.1 molar HF and 0.05 molar NaF. Is that a good ratio? Now, we would like these to be equal, or at least no greater than 10. So 0.1 divided by 0.05, I guess that's only 2. Sometimes you don't know till you do the math. Okay, so this is twice as much as that, so that's okay, that's within 10. But what's going to destroy the buffer? So we have 3 choices here plus none of the above. So let's look and see what's different about these. Well, they're all adding the same amount the same number of moles of stuff, right? What they're adding is different. Here we're adding a strong acid, here we're adding a strong base, and here we're adding a salt. Does this salt have any acid-base properties? So the ions in there are sodium and fluoride. Sodium's not going to do anything. It's the counter ion of a strong base, sodium hydroxide. But what about fluoride? Remember, anions can be conjugate bases of acids. This is the conjugate base of which acid? HF? Strong or weak? Weak. Because that's a weak acid, this will act as a weak base. There might be questions like that on the exam today. So if we're adding NaF, oh, look, there's already NaF in there, and there's less NaF than HF. Is that going to destroy the buffer? No, it's actually going to make the buffer better, right? Because this is 1 liter, it has 0.05 moles, and if we add another 0.05 moles, now we'll have the same concentration of acid and base, and so that'll be really nice. That's not going to destroy the buffer. Now we've got a choice between a strong acid and a strong base. The acid in our buffer neutralizes base. The base neutralizes acid. Which one do we have less of? We have less of this guy. This is the conjugate base. It will neutralize acid. So we have more more weak acid and less weak base. So which one's going to get overwhelmed more easily? The one that there's less of? This one. There's not as much of this. So this is the part that neutralizes acid. So if I add 0.05 moles of HCl, that's going to take all of the NaF to neutralize. And there won't be any left to be a buffer. So it's this one. Any questions?